So, the clock is already ticking, so I better start. Hi everybody, welcome to this session. It's about a new programming language known as Go. My name is Stoyan Rachev. I work at SAP as a software architect. Throughout my career, I have been using several programming languages, starting with C and C++. The main part of it, however, was spent with Java and JVM-related stuff. Recently, in some projects, I encountered Go, and I found it quite exciting. I had quite some fun with it. So I thought my experience could be interesting to other Java developers as well. And this is how the idea about this session was born. Let's do a short warm-up. How many of you consider yourself Java developers? Okay, almost everybody. That's good. I see I'm in front of the right audience. Anybody having any previous experience with Go? Okay. Not Go, which is also good because this session is really quite introductory. Let's see what's in store for today. So, as you can already assume, we are going to introduce Go from a perspective of a Java developer. So we'll be using our knowledge of Java quite a lot to make things easier. We will start with a short introduction, trying to answer questions such as why Go, what is Go, do a comparison with Java, and so on. And then dive into the details of the language, the different features that the language has, and through all these points that you see on the slide. I hope you understand that presenting an entirely new programming language in 50 minutes is not that easy. And therefore, I will be assuming that I will be skipping a lot of things. So glossing over a lot of detail, particularly in parts where the two languages are similar to each other. I am also not a great believer in teaching a programming language just based on slides, so I've prepared a few simple but working examples that we'll also take a look at, and to see a little bit Go in action, to give you a feel how Go programs may look like. So what is Go? By the official definition from the Go's website, Go is an open source programming language, originally from Google, that makes it easy to build simple, reliable, and efficient software. Sounds great, like. And this mascot, this is Go's mascot. It's a tiny rodent that lives only in North America, as far as I know, and its name is Gopher. In Bulgarian, it's гризач от семейство гоферови. Okay. So, why Go? Why create an entirely new programming language? For what purpose? And the answer from the language designers is we needed to address issues of scale. And when they say scale, they mean both system scale, such as number of machines, number of parallel jobs, and engineering scale, such as number of developers, number of projects, number of lines of code. And the scale at Google is very big. They found that traditional programming languages that they mostly used C and C++ actually, did not help them achieve that scale. And they addressed that challenge by creating an entirely new programming language. And this is, they seem to have hit a sweet spot because the language has become increasingly popular in recent years. And it's currently ranking at something like number 15 at the so-called red monk index, what you can see on the slide, and about number 40 in the TIOB index. And its race to those positions has been very, very quick. So it's really around just for a couple of years, basically. And it's really interesting why this has happened, because Go is, as you will see, not really a general purpose language, not really a scripting language like Ruby or Python. It's not JVM compatible, so it doesn't interoperate with Java. And in its original niche of system programming, it has a very well-established competitor, such as C and C++. Okay, so before we go on, I would also like to address the question, so why Go for Java developers? After all, Java is number one in all possible rankings and unlikely to be replaced anytime soon. And so why should we Go instead of just go on with Java, you know? And I see three possible reasons. First of all, I strongly believe that learning new programming languages makes us better programmers in whatever language we chose to code in. So I actually strongly recommend looking at other programming languages, not only Go, also Scala, also Kotlin, also all the other interesting things are out there, because this really makes us better programmers independently of which language we decide to code or we need to code in. Secondly, Go may be a better choice than Java in many situations, especially if you need to write something that falls into the category of a system or infrastructure component, something like a router or a reverse proxy or a compiler. You probably can use C and C++ for that, but as you will see, Go is much easier to learn, compiles much faster, and has a number of other advantages. And finally, how we first came into contact with Go at SAP is that we needed to do some stuff for Cloud Foundry, interoperate with Cloud Foundry components, integrate with Cloud Foundry, and we found out we have to do it in Go, because almost the entire Cloud Foundry now is written in Go. And the Go has been embraced by the communities around a few very popular projects, including Docker, for example. So having in mind the rising popularity of the language, you may find yourself in a similar situation soon. So I guess now it's a good time for you to take a look at this language and anticipate a little bit what might be coming. And now let's look at similarities between Go and Java. And there are a lot of them, actually, which makes my job very easy, I know. So first of all, both are sys-style. This will make the Go syntax largely familiar to you. Both are imperative, although in Java 8 we have some functional stuff added. Java is traditionally an imperative language, so is Go. Both are compiled. Both are statically typed. Both are object-oriented, although Go's approach to object orientation is really different, as we will see later. Both are cross-platform, both have garbage collection, it's a great feature, both have memory safety features, both have type assertions and reflection. However, there are also a lot of differences. And Go has some stuff that Java doesn't have. So first of all, Go doesn't have any VM, meaning that all code is compiled to native code and executed on the processor directly. There are some syntax differences. There are built-in strings, arrays, and maps in Go. As I mentioned, these are some additional things that Java doesn't have, but Go has. Go has type inference, very convenient feature. Go has closures, real closures. We'll see the difference. Go has concurrency built into the language in a very, very interesting way, not to be found in almost any other programming language, very different from what you find in Java. But even more interesting than the things that Go has All those things that Go doesn't have. And that's a pretty long list. So Go has no classes. There is also no inheritance, consequently. There are no exceptions, there are no annotations, and there are no generics. And there are more no's, no place on the slide to fit them. So there are no overloaded methods, for example. There is no final keyword or any concept of variable immutability. And so on and so on. And now, let me guess what you might be thinking. So here is the language that is on one side very similar to Java. On the other side, it doesn't have most of the features and has even omitted most of the interesting one, not to mention languages like Scala and Kotlin that build upon and add even more features. And no classes? Are you kidding me? So probably you are now seriously considering switching to the other session. Well, I understand that. I went through the same kind of cultural shock, to be honest. And what I can say is, please stay here. Hopefully, you will find it quite interesting after all. Okay. And now, before we go on, let's try to immediately answer the question, okay, why is Go so different? As you can see, Go is not feature-rich. It's actually the exact opposite of feature-rich. It's a rather minimalistic language. And if you were wondering whether it was designed in 6 or how many it was, 15 days as JavaScript? No. I mean, this was really a work over several years. Every decision, what should go and what shouldn't go into the language, was very carefully considered, very deliberate by very experienced engineers. And they had a list of goals that they wanted to address. And the guiding principle was anything that really fits these goals goes into the language. If it doesn't, then it doesn't go into the language. And the goals were, they described this as language design in the service of software engineering. So they wanted to create a language that is familiar, yet it's modern, meaning that it has built into the language features that you need to do modern programming. So if you need to do concurrent programming, better build that into the language, give you a toolkit that is easy to use for that, instead of doing that into a standard library. The same for arrays and maps and so on. They wanted to have very high performance, both compile and runtime. And the compile times for C and C++ programs was one of the strongest motivators in the very beginning. They wanted to have a good balance between complexity and convenience. And they carefully measured each feature. Each feature is adding complexity. So does it add enough convenience to justify its inclusion into the language? So they consider that, for example, for garbage collection. Yeah, garbage collection is extremely convenient, extremely important, even though it adds complexity to the implementation of the language. But they said, okay, it simply has to be in. However, when they look into inheritance and classes, well, you can do object-oriented programming without that, actually. Many object-oriented patterns or principles actually advocate favoring composition over inheritance. So they thought, okay, that will really increase the complexity of the language, maybe not add that much convenience, let's leave it out. And this philosophy is summarized in one sentence: less is exponentially more, by one of the language designers, Rob Pike. And I think they did a remarkable job here. They really they created a language that is very consistent, that is small and elegant, and that enables programmers to accomplish a lot using code that is really understandable and easy to read. So before we go on, let's look at a small example. And wow. That's really interesting. Okay. And this is the Hello World program. So we have a package declaration at the top of the file. Then we have an import, which imports another package. It's called FMT. Package is Go's approach to handling dependencies, and it's pretty simple. We have a function, predictably called main, and this function, the only thing that it does is calling another function from the FMT package that prints hello world to the console. You see, syntax looks familiar, nothing surprising so far, and let's continue with the slides. Now let's dive a little bit into the features of the language. So you can judge for yourself what are we talking about actually. Variables and constants. So in Go, declaring a variable, you have to use the var keyword. And the type will succeed, not precede, the variable name. But you can also omit the var keyword and use this colon equals if you will be immediately initializing the variable, and you can also skip the type in this case because there is type inference. If you don't initialize the variable, it will get a default value that is the 0 value of the corresponding type, very similar to Java here. And you can also declare constants. Constants, unlike in Java, these are computed at compile time, and they can only be of one of the basic types. There is no any analog of static, final, public, and so on in Go. Everything is static by default. There are no classes, remember. There's no final. And public, anything that starts with an uppercase letter is public. Everything that starts with a lowercase letter is not public. As simple as that. Okay, now let's look at control flow constructs. The basic for is the same as you might expect, except that there are no parentheses. Similarly to other languages, we can skip the first or the last or both, and that converts for into a while loop. And for this reason, there is no while loop in Go. Why? It's simply not needed. We have for. And interestingly, you can also skip this one. And can you guess what we get here? Yeah, it's an infinite loop. So let's look at if. So if is again very similar. No parentheses. However, we can do this in Go. So put a variable and initialize it in the if statement itself. And notice how this brings it closer to for. It's actually exactly the same idea, and it's very consistent between both constructs. And then switch. If you look into the syntax of the switch, again, it's very similar. There's no automatic fall through. However, this is also possible, meaning you can put anything in the cases, any expression, not just constants. This is also possible, meaning you can initialize a variable in your switch and switch over it. This is, again, very similar to what we have in the other constructs, the for and if, makes it consistent. And also, you can use any kind of expression in the switch itself, including the true constant, which is has a shorthand form for this. And if you look closer, you will see that this is actually the same thing as chaining if and else statements, so if else, 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 can be achieved with a switch, and it's a little bit more concise and therefore preferred in so-called idiomatic Go. Yes, you can, but this is something I'm not going to talk about because it's a little bit more advanced. So let's look at basic types. So Go has basic types. There are strings, of course. There are sequences of UTF-8 characters that are also known as runes in Go. There are booleans. There are integers. And let's do a short test. How long is an int in Java? Who thinks it's 32-bit? Who thinks it's 64-bit? Who thinks it depends on the platform? Okay, good. It's 32-bit. In C and C++, however, in Java, yes, exactly. In C and C++, however, it depends on the platform. And in Go, it also depends on the platform. However, Go also has this types that have the exact number of bits, like int 8 and int 16, that correspond exactly to the Java types. So if you want to be precise about the length, it's also possible. And more interestingly, Go also has pointers, similar to C and C++, and unlike Java, here we are declaring a pointer to a string and initializing it with the address of the string S. However, unlike C and C++, there is no pointer arithmetics, and you don't need to think about the memory, actually, because memory safety is built into the language. It's perfectly safe, for example, to create a variable in a function and return its address as the return value from that function. Pointers in Go are actually very similar to references in Java. It's just a different syntax. The main use of pointers is being able to pass memory, to pass large data sets efficiently around. The same why Java has references. Now let's look at arrays. Go has arrays, but the length of the array is part of its type, which makes them not really useful in practice. And this is not a problem because Go also has slices. So slices are actually similar to array lists in Java, but they are built into the language. In the slide, we are initializing a slice that has A as its underlying array using the slice operator, bracket, colon, bracket. And this slice now can be grown dynamically and manipulated dynamically, unlike the underlying array. We could create a slice with the same contents by using the so-called slice literal. And we can also use the built-in make function to create a slice with a certain length, and then use the built-in append function to append elements to the slice. Then we also have maps, and they are very similar to Java hash maps, so pretty much the same thing, except that they are built into the language. We have to use the make operator to create a map, the make function, sorry. And here we are creating a map from string to int, and initializing some elements. And we could do that with this map literal as well. And taking the element of a map is always safe, because if the element is there, you will get the value. If the key is not there, you will get the 0 value of the corresponding type. That's very convenient and makes map very easy to use in practice. However, what if you really want to know if the key is there or not? Then you can use this kind of syntax to check if really the element is in the map. finally, you delete elements with the delete function. It's important to note that maps and slices are reference types, meaning we don't need a pointer if we want to pass them to a function that wants to modify them, right? So it's exactly the same as in Java, so it's intuitively what we expect as Java programmers. Okay. Structs. Structs are the Go's mechanism to compose types out of simpler types. And they are similar to Java classes, but they are not classes. They are also very similar to C structs. And here we have a struct with two fields, x and y, and we create a variable of this type, point, and initialize it using this struct literal syntax. And we are also using one of its fields by using the dot syntax, so nothing special so far. However, structs are not reference types. So if we have a big struct, how do we pass it around? Via pointers, yeah. And interestingly, we can take the address of the map literal and use it as a pointer to a point. And the syntax for addressing the fields is exactly the same. So it works with values, and it also works with pointers to structs. And let's look at another example. And this is a small program that does conversion from meters to feet and other metrics. So we have two const decorations here after the imports. We have an output variable that will hold the value of a flag that we will pass on the command line. After parsing the flags, we will iterate over all the remaining arguments using a for loop and the so-called range operator that I did not introduce so far because I wanted to show it here. And we are basically iterating over all the elements of a slice called OS args, starting from n. And then for each of these elements, we will parse it to a float using this function here. We will talk about error handling in a minute. And if this is successful, we then switch over the value stored in the variable output, which, as we see, is not a string, but actually a pointer to a string. So we dereference the pointer by using the star operator. And if it's feet, we will convert to feet and print it out. If it's inches, we will convert to inches and print it out. And let's run it. Let's see how this actually works. So to run it, I can do it in several different ways, but what I do now is go run and the name of my source file. And then I will pass a parameter, let's say feet, and a number. And this 10 meters converted to feet. Can do the same with inches. Notice how fast everything happened. What happened is that the Go compiler compiled my program into an executable, and immediately it got executed. And yes, of course, it's a very simple example, so it's not much to talk about. But Go's compilation is extremely fast, also for very large programs. So you would get a few seconds of compile times as a rule, basically, no matter how big your program is. Okay. Let's go on with the language features. Now we come to functions, and functions in Go are similar to static methods in Java, and there's really not much to talk about. I mean, should be already familiar to you, except some syntax differences. The idea is the same, everything is the same. However, there are also some differences, and the most notable one is that functions in Go can return multiple values. And the thing that this is used most often is error handling. Now, error handling in Go is very different from error handling in Java because, as we already mentioned, Go doesn't have exceptions. So, unfortunately, since we have multiple return values from a function, this is really less awkward than in other programming languages that don't have this feature. So the idiomatic Go is basically goes like this. Whenever you want to signal an error, you will return a value of the type error. Error is an interface. We will see later what it is. And that will be non-null. And if you want to simply normally exit from the function, you will return null as the error. So far, so good. Unfortunately, the syntax of checking for errors is every bit as awkward as in other programming languages that don't have exceptions. So if you want to program correctly, if you want to program safely, you have to check the return value from every function that may return an error, and these are the majority of the functions out there. And if the error is not new, do some proper error handling, propagate the error or something like this. And this was a deliberate design decision that I need to talk about a little bit, because it's really strange. It's too strange to me. I tend not to like it. Here's what the language designers say. They say exceptions are misused most often, or very often. Programmers tend to label normal things like failure to open a file as exceptional, and they tend to forget or don't do error handling properly when doing exceptions, because they're not forced to. It's simply too easy to propagate the exception to a higher context, until it pops up into the face of the user with an error message that is completely not understandable. They wanted to stop this, and their decision was no exceptions. Well, I have some problems with that, but that's a personal thing. Closures. Go has closures, and they are real closures, not lambda expressions as in Java. Who knows the difference? Okay, so the difference is that with closures you can modify external variables, unlike lambda expressions. And here is what we actually do here. We have a function Fibonacci that returns another function. So functions are first-class citizens, can be passed around, of course. That returns an int. And this function will modify the values of two external variables, x and y, in such a way that if called repeatedly, it will return different values. And they will happen to be the Fibonacci numbers in this case. Defer is a very useful construct, also related to error handling. In many situations, we need to do proper cleanup independent of the way we exit a function, especially if we rely on return values to signal an error. We need to make sure that this cleanup is executed properly every time. So this the same idea as finally in Java. In Go, we don't have finally, but we have defer, which means we can defer the function call to the very end of the function execution, and it will always get called, no matter how the function finishes its execution. So in this particular example, we are getting a URL, and the result is returned in this variable resp, but the body of our response needs to be closed explicitly, and to do that, we use defer, a very traditional thing to do in Go. Methods. Now, we don't have classes, but we have methods. And this is where things start to get interesting, because here in the slide, we are creating a new type called stack, which is actually a struct. It uses an underlying slice of types slice to string to hold the data. However, there's also a method attached to that type, and it's a normal function, except that it has a receiver that is before the function name. And this receiver is not even stack, it's pointer to a stack. And we can use this receiver inside the body of the function in the same way we would use any of the arguments. And what is quite interesting, this type definition here, we are using a struct, but we could actually attach a method to any type, including built-in types, including library types. Since we have no classes, all classes or all types are open, so to say. And this becomes really interesting if we combine it with another feature, namely interfaces. Interfaces are very similar to interfaces in Java in many respects. So, for example, here we have a library function, fprintf, and the first argument of this function, w, is an interface. And here's the definition of this interface. It's just one method, of course. So we can pass as the first argument any type that satisfies the interface. What does it mean for a type to satisfy the interface? And now this is where it gets interesting, because there is no implements in Go. Interface implementation is implicit rather than explicit, meaning that we can create a type, add the methods of the interface to that type, and immediately we are satisfying the interface. This makes it very, very convenient to change your design later on in the process. You can make types that you don't want to change, or you cannot change, satisfy your interfaces. And it's all very flexible. And here is how we would use the interface. So create a variable, then use its address to pass it to the library function fprintf. And that won't do anything, because as you see, our implementation is a no-op implementation, but it will compile and run. Okay, skip over this example, timing reasons, to have more time to talk about Go concurrency. I think concurrency in Go is one of its most interesting features, and it's best expressed by a kind of mantra that says, don't communicate by sharing memory, instead share memory by communicating. And before we go on, we all know what the problem with doing concurrency correctly is. The problem is called shared state. And this is also the reason why many programming languages, including even Java as of late, strongly encourage immutability and use immutability to promote that safety when doing concurrency and avoid the inherent problems when mutable state is shared between different pieces of code that execute concurrently. However, we don't have this problem in Go. Why? Because Go uses a model known as communicating sequential processes for concurrency that avoids it, simply. And there are three parts to this model. First is the so-called Go routines. And Go routines are very simple. They are just normal functions, except that you can, instead of just calling a function by its name, you can call it by Go its name, and then it's executed concurrently. in parallel to your other code. For example, here we say go say hi, and they say there. What will happen? Will it say hi there, or will it say there hi? Hi there? Who thinks it will say hi there? Okay, very few people. Who thinks it will say there hi? Very few people. Well, all the others are right. I mean, we cannot say because we don't synchronize them in any way, and therefore it's absolutely unclear what will happen. Both outcomes are possible. And how do we synchronize? We use a new construct, which is known as channels. And channels are simply a typed construct with which we can pass information from one Go routine to another. Here, we are creating a channel of type int, so we can only pass ints through this channel, not anything else, using the built-in make function. And then to send something over the channel, you use the send operator, which is simply an arrow pointing to the left. And to receive something from the channel, we use, again, the arrow, but this time we put the variable on the other side. And here we receive and assign something, and here we can receive and discard the result. Both are legitimate. And the interesting thing about these send and receive operations is that they are blocking. So when you send something, somebody has to receive it on the other side before the execution of this Go routine can continue. And the same is for receiving. If you start receiving something, there must be somebody sending. And only when something is really received, this Go routine will continue the execution. And this makes channels your favorite and perfect synchronization mechanism. You can close a channel to signal that nothing will be sent over it, but know that this is not really mandatory. Closing a channel is not like closing a file. You can leave it open. It's no problem. And the third element to concurrency in Go is select. Quite often, you will be in the process of doing communication for several different reasons, possibly with several different Go routines, and we would like to execute whatever blocking operation is ready to be executed first. And this leads us to a construct that is very similar to switch, except that instead of switch, it's called select. And instead of, and in all the cases, we have to put either send or receive operations. We can also have default, so if neither of the cases is ready to execute, it will execute the default. If there is no default, it will block until any one of the cases is ready to execute, and then it will execute it, only it. Usually you put that in a for loop, and then you have a Go routine that is properly synchronized and efficient, communicating with several other Go routines. You can use these building blocks to build many interesting concurrency patterns. Just one of them is what is known as pipelines. So here in the example, we have one Go routine, which we call the generator, that generates all the numbers from 1 to 10 in this case. Note we are creating a function value, then immediately use it to invoke in a Go routine. And then we have another Go routine. This is the invoking Go routine, which is the printer that prints the values. The values are sent over the channel, that is numbers. Now, I would like to show this, to a little bit expand on this example. And I have a program. Let's look at the source code. That is also about pipelines. But each stage of the pipeline here has actually two channels, one for input, one for output. If both are not new, the stage will simply receive a value from the input channel and send it to the output channel. If the input channel is new, this is our initial stage, we will receive values from a channel that will simply send us values each second. And if the output channel is new, this is our last stage, we will print out the difference in time between the value and the current time, so the time it took for the value to traverse the entire pipeline. And here we have some setup code. I will not go over it. But the important thing is we have a number of pipeline stages, and we can also use a command line argument to initialize this number. So let's see how this works. I will run now go run pipelines, and I will pass just 10, which creates a short pipeline of only 10 stages. And this is the time it is needed for the value to traverse the entire pipeline. You can also do that with 100 or with 1,000, let's say. Now it takes a little bit longer to traverse the pipeline, obviously, because the pipeline is now 1,000 stages. Now, how about 1 million? Have you ever tried to run 1 million threads in your JVM? You can try it. The result will not be very successful. But here, interestingly, our pipeline works, and it takes half a second for a value to traverse it from the beginning to the end. And this is not a mystery. The reason is that Go routines are not threads. They resemble threads. You can think about them as lightweight threads and reason about them as threads, but they are not threads. They are other things. They are scheduled by Go's runtime over a number of pre-allocated threads. And this switching of context is very cheap, as you can see. And this is why you can get incredible performance of this channel's receive and send operations. Okay. Now, tools. Tools are not part of the language, but we have to mention them because they are an integral part of what you will be dealing with if you start programming in Go. And Go's implementation has built-in tools for most common tasks you would need. So for running your program, you already saw. For building your executable, so you don't need anything like Maven. It's just built into the language toolkit. For testing, for formatting your code, and for also dealing with dependencies. And we are nearing the end of the session. And so I would like to just outline, if you are curious about what you saw, if you want to learn more, you can go to Go's website. It's the definitive source of more information. There is an interactive tour. Very nice, very easy to get started with the language. There is an FAQ that answers all those questions. Why Go doesn't have whatever? What is the best way to do whatever in Go? So it's definitely worth taking a look. And if you want to get more in-depth knowledge, I strongly recommend this book, The Go Programming Language, by A. Donovan and B. Kernighan. And if you wonder who B. Kernighan is, maybe some of you have heard about Kernighan and Ritchie. They are the authors of the book, The C Programming Language, that came out in 1978, so almost 40 years ago. And yes, that's the same Kernighan. And now the book is called The Go Programming Language. Maybe that tells you something. Okay, a couple of final words. So Go is similar to Java, yet very different. I hope this does not make you disappointed. That just makes you curious. If it's the case, I'm really glad. Go is simple, elegant, and efficient. And finally, I really think Go is worth giving a try. And with that, I'm open for questions. There's a question.
I have a statement and a question. The statement is I personally did not like the language. It is right only, it uses some operators, not keywords, but okay. My question is about the immutability. You did say that structs are initially not passed by reference. So is that by the Go developers' advocacy for not passing them by reference and just create new structs or just attach them as a reference methods as is shown?
The short answer is no. Go doesn't have any preference for immutability. It doesn't encourage immutability in any way. And yes, that might be different from what you have seen and from what you have heard in many other sessions. The reason is, I mean, there are many reasons, I guess. One of the things that I mentioned, if you strongly favor immutability because of ability to do concurrency in a better way, that's a very valid reason. However, in Go, that's simply not necessary. And with CSP, you just do everything without immutability. You don't share state because you don't need to share state, and you're fine. That's the long answer.
Okay, thank you.
Sorry, but the next sessions have to start after 5 minutes.
Thank you very much.